Welcome back, fellow aircraft builders and aviation enthusiasts. In this episode of Drafting Basics, we will begin discussing how to read and interpret a set of Zenith Aircraft Company blueprints. Today we will look at sample drawings from my set of STOL CH750 blueprints, but most of the information I discuss is applicable to any set of blueprints. We will be talking about a drafting concept called orthographic projection and why it is relevant to Zenith drawings. We will also touch on some fabrication issues that arise when interpreting the drawings. In future videos, we will look at more complex parts and assembly drawings. Please keep in mind this is not a comprehensive series on how to be a draftsman. I'm focusing only on what it takes to read Zenith aircraft blueprints and draw their parts onto raw stock or templates. There's a lot to cover, so let's get into it. When you first look at a set of blueprints, they can seem overwhelming due to the amount of information they contain. A good set of blueprints contains various types of drawings that depict complete information on parts dimensions, material specifications, hardware sizes, and assembly. The information should be complete enough to allow you to fabricate each component of the aircraft from scratch, and specify which standard hardware like nuts, bolts, and manufactured components are required. A good set of blueprints omits as much duplicate information as possible, but this sometimes makes information difficult to find. Often, the way dimensions are presented will require you to do some calculating and figuring in order to physically make the parts. Information on things like bolt holes and sizes or assembly may be located on different pages of the blueprints. These things are done to minimize the clutter within the drawings and yield a clean, orderly representation of the design. Drafting is the general term used to describe the act of creating a technical drawing or set of blueprints. Drafting is also the process we use to lay out parts using precision instruments and tools at the beginning stages of fabrication. Any set of technical drawings will contain symbols, perspectives, units of measurement, notations, and other information needed to physically create what is shown. Drawings of individual parts consist of boundary lines, hidden lines, and measurements for locating specific features of the part, such as holes, bend lines, machined areas, and other bits. Zenith blueprints are very easy to read because they only use a few simple notations and symbols. Their blueprints are designed to be used by the average home builder, and you don't need to be a machinist or engineer to understand them. However, there are a few basic things that are helpful to understand when interpreting a set of Zenith blueprints, and that's why I created these videos. One major concept in drafting is a type of drawing called an orthographic projection. Orthographic projection is a way to represent a three-dimensional object in two dimensions on a piece of paper or a computer screen. When you look at different views of parts in a set of blueprints, you normally see some variation of this type of drawing. An orthographic projection is so named because it projects one or more surfaces of an object onto two-dimensional viewing planes or angles to show details of the object. This type of drawing allows the designer to detail any side of an object with enough information to fabricate it. The needed number of projections depends on the complexity of the part. I won't go into the technical geometric terms used to fully explain it, but it is the foundation of how most of the technical drawings are presented in a set of blueprints. Although it is not difficult to learn, understanding the basics of orthographic projection makes it much easier for us to interpret a set of blueprints. In reality, Zenith uses several types of drawings to present information to us, but the parts layout and assembly diagrams are mostly variations of orthographic projection. In the first few videos of this series, it will not be entirely obvious that we are looking at drawings rooted in orthographic projection. Because of the simplicity of many of the parts, Zenith is able to use just a single view or projection rather than multiple projection drawings to provide enough detail to make the part. You will see sheet metal parts drawn in their stretched or parts blank flat state, and then maybe a side or top view in the formed state. Although many of these are not true orthographic projection drawings, they are still rooted in that method of creating a technical drawing. However, once we start looking at assembly drawings and more complex parts, you will definitely see clear examples of orthographic projection. A real quick disclaimer, I am not a draftsman by trade. I received several years of schooling on drafting and computer-aided design in the late 80s and early 90s, but I ultimately chose a different career. It's ironic, though, that even after almost 30 years, I felt more comfortable reading blueprints than doing actual fabrication when I first started this project. However, I may not use all the correct terms or technical language used by professionals. I'm simply trying to make the information as easy to understand as possible without getting bogged down in technical vocabulary and theory. So with that in mind, let's take a look at some drawings. Okay, so here I've laid out just a very quick sample part, and this is not something that's out of the airplane, and this is not something that you need for the airplane, just something I whipped up. It's very simple geometry to illustrate a few points. If you look in the three-dimensional view up in the corner, this is an isometric drawing of this sample block. It's basically a picture of what the part is supposed to look like when it's complete. We have a front face, a side, and a top. If we were going to do an engineering exercise on this particular part, or a drafting exercise, normally you would take an isometric view of it, and then you would draw at least 3 sides of it in orthographic projection. So down here I've got the very front face of this part, so if you were staring directly at the front of it and you couldn't see the sides and it wasn't rotated in any way, but you were staring directly at the front face of it, this gives you what you would see, and then a few dotted lines that show hidden features, and in this case those are simply the bolt holes. Moving over to the side, this is a projection now. We are projecting these feature measurements over here, and I don't know if you can see in the drawing, there's very light lines. Those are the projection lines that go across that correspond with those measurements. So here we have this shoulder or flange out here that has the bolt hole in it, and this line is projected all the way across here to denote the edge of the flange on this side drawing. And then the bottom of the piece, we have the bottom edge here. The bolt hole is manually drawn in, and then we have a dotted line here which represents this interior feature that you can't see from this view, as well as the dotted line for the bolt holes with the center line. And then we've got a series of cumulative measurements over here. So rather than having 2 line measurements, we have one datum line here, a 20 millimeter measurement from here that denotes the shoulder, another 20 millimeter measurement here that denotes the height of the part. Back over on the front view, we have a measurement from a datum line here that indicates that this part, this interior feature is 10 millimeters thick. Normally you don't see a lot of measurement and datum lines that reference themselves off of hidden feature lines. Most of your measurement lines are going to go up to a solid line that is part of the visual plane that you're looking at. Moving up, again, we have a series of very faint lines up here. These are projection lines going up to where the top view of the part is. That's why this is called orthographic projection. We are projecting the views in different planes so that you can see where the relevant information is. I've got a couple of datum lines here that denote the dimensions of the part. Here's the solid outline of the part. We can see from this datum line that it is 15 plus 15, so it's 30 millimeters wide, which is why there's no reference line down here. We can see already right here that this is 30 millimeters wide. We know that because these are 15 and 15, that the center line of this part is where these bolt holes are located. Moving up to the top datum line from left to right, we've got 10 millimeters to the center line of the hole, 10 more millimeters to the edge of this shoulder right here. Then that shoulder is 10 millimeters thick. We have that's actually wrong. That's supposed to be 40. Let's fix that right now so I don't have to re-record all this. We know that the cradle of this part is 40 millimeters wide, and then it's another 10 millimeter thick shoulder, 10 millimeters to the center line, 10 more millimeters to the outer edge of the part. Now in Zenith drawings, often you will see what I call stacking or cumulative measurements, where you will not get a measurement from the datum line for each measurement going out there. It clutters up the blueprints and it takes up a lot more space on the page to write a measurement line for each feature off of a single datum line. So in this case, if we were going to have that visible to us, we would see 10 millimeters to the center of the bolt hole, 20 more millimeters over to the edge of the shoulder, and then another line noting 30 millimeters, and then another line noting 40 millimeters to the next edge of that shoulder. So you can see we would have many lines stacking up here on top of our drawing that would show a whole bunch of locations when it's more efficient and cleaner to list them this way. Now the problem comes in later when I'll show you when we're laying out parts and when we're talking about measurements. The problem comes in being accurate when you're laying out cumulative measurements like this. You either have to do some math or you have to be extremely careful with how you measure cumulative measurements off of one measurement. So let's say we laid out the scale here and measured 10 millimeters, and then we moved our scale over and measured another 10 millimeters. And I'll get into more details on these measurements, but you have to be careful when you start using datum lines for reference points in a cumulative fashion, because there's going to be an extra margin of error because of the placement, the manual placement of your scale on the sheet metal. And then the last dimension down here is simply how the diameter, so the circle with the slash through it is how you denote a diameter. If it was a radius dimension, it would just be denoted with an R. And then it tells you diameter 10, so we know that this bolt hole or this clamping hole is 10 millimeters in diameter, and we know again it's a diameter because it's denoted graphically here with two arrowheads pointing to the full diameter of the hole. You could also, if this was denoted by radius, you would have an R here, and then your arrow line would terminate right at the tip of the hole here with just a single arrowhead and show radius of 5, and you would not have the center line denoting the diameter. So essentially, this is like 90% of what you need to know to be able to understand Zenith blueprints. We have very simple datum lines. This is how you read these drawings. This is an orthographic projection. Zenith's drawings are basically orthographic projections of their three-dimensional parts with some additional instructions on how to form those parts or fabricate those parts, what the material has to be made out of, and things like that. So you have to have a solid foundation on how to read this type of a drawing in order to be able to fabricate parts from a Zenith drawing. Again, I don't think this is very complicated, but if you've never seen this kind of presentation before on how to read blueprints, the first time you crack open a set of Zenith blueprints, you might be overwhelmed with the amount of information that you see. So let's take a look at the Zenith blueprints now, and we'll show you exactly what I've been talking about. First off, I'd like to have a little disclaimer here. I do have permission from Zenith Aircraft Company to use example drawings in my videos from them. I'm not sponsored by Zenith, and I don't make any money off of my videos at this point. I don't have my channel monetized or anything. So I have permission from the company to use these drawings for educational purposes in my videos, and I don't receive any compensation for that. This is just to help builders be able to interpret the drawings, and hopefully if they're scratch building, have a little easier time figuring out how to read things. When you get a plans package from Zenith, one of the first few pages that it's going to come with is a general information page. So before you even start looking at drawings, they're going to tell you how their blueprints are numbered, what all the details mean, revision numbers, the part number on the drawing, the part label itself, what aircraft it's applicable to, and things like that. So for example, if we look at, this is my blueprint drawing, this is my package of blueprints for my Edition 3 Zenith STOL CH750. This is basically telling us how the information is presented in their blueprints and how to read it. The horizontal stabilizer front bracket itself appears later in the drawings because it's part of the tail assembly when you start fabricating that part. So they give you a parts geometry legend that gives you labels. It's basically a key that tells you what things are labeled like. So L is length, DL is developed length, R is the radius, like I talked about in my example. The little theta symbol or 0 with a slash through it denotes the diameter of a part. A lowercase t is the material thickness. And then of course they tell you, unless specified, all measurements are in millimeters. Now the one thing about Zenith drawings is almost all your measurements that you're going to be, when you're laying out parts and fabricating them, almost all of those are going to be in metric. They're going to be presented in metric. And where the plans deviate from that are places like where you have bolt holes that use standard imperial measurements, like the Army Navy specification, the AN hardware that we use, that's all done in like 1/16 of an inch or 1/8 of an inch. And the thickness of the material that you're using, at least here in the United States, is generally given in thousandths of an inch. So your standard part thickness might be 25 thousandths of an inch. That's the thickness of the stock that you're using to fabricate the part. But most of the measurements that you're going to be drawing onto the piece of stock or laying out on a form block or laying out for some type of fixture is going to be done in millimeters. So that's what they're telling you here. Unless specified, all measurements are in millimeters. Looking over here at the sample part, we have the horizontal stabilizer front bracket. Noticing down here, this is an example of what the part appears like on the page later in the drawings. They're giving us cumulative measurements here, so we don't have an overall length of the part listed with its own measurement line. We have cumulative measurements, 104 millimeters plus 35 millimeters. We have all the information presented to us that tells us how big this part blank has to be. And then up here they've told us how it needs to be formed. It needs to be, when it's finished, 25 millimeters by 25 millimeters with a radius of 6.4. That's actually a 1/4 inch radius with a 98-degree bend angle. So this is the flat part here. This is how we cut this part. and then this is how it's formed when we're done. You'll notice here we've got a line that is, it's not a normal dash line, it's got a long line and then a small dash and a long line and a small dash. That typically is going to denote a bend line rather than a hidden feature. It's either going to be like a center line, which is a reference line, or a bend line, rather than just simply some kind of hidden feature like a bolt hole that you can't see from this view. So that's something to keep in mind on a lot of these flat pieces. So here they've laid out the dimensions that we need. Now if we were to cut this out of a piece of 63 thousandths inch thick, they've told us down here what the part name is, the revision number 0, the part number on the drawing page itself, or the assembly, which is part number 4. They're telling us here that this is supplied pre-drilled, and that's only if you buy it in the kit. Remember, if we're scratch building, of course, nothing is pre-drilled. And then they're telling us material information quantity required with the 63 thousandths of an inch thick, 6061 T6 alloy. You need to make one left and one right part. Now, on these parts here where you have to make a right and left bracket, you have to make mirror images of these parts, and it's up to us to figure out how we're going to do that. But again, calling your attention to this, one thing you may notice right off the bat is that these flanges are 25 millimeters long when the part is formed, but yet they've only got 24 millimeters here and here, denoting the part when it's in its flat condition. The reason for that is when you bend a piece of material around a radius, this isn't the correct way to say it, but the part essentially gains length as it goes around a radius. If this was a very hard, sharp 90-degree bend, then you may end up with short flanges at 24 millimeters. But because this is going a shorter distance by going around a curve, you need less material once the material forms around that curve to get to the 25. So in a lot of drawings, you're going to find that the dimensions before the part is bent are going to be shorter than what they should be once the part is formed, and we'll get into more detail on that later. Over here we have an example part. Now this is called standard L. They tell you that it is designated as L with a circle in it throughout the drawings, and we cut to length as desired. Now with Zenith's highly refined kits that they're shipping, they are pre-drilling all the parts for most of the things that you receive in the kit, and it's my understanding, although I haven't confirmed that they are also experimenting with pre-measured, pre-sized pieces of L angle that are pre-measured, pre-drilled, and pre-cut to bolt together for the kit so that you don't have to use these. So some questions have come up as how much L do you need to fabricate this airplane, and I think in my one of my previous videos I figured that I needed 64 pieces of standard L, which of course seems like an awful lot of standard L. But the way that I came up with that number is I got on their website back in the day when the Edition 3 plans were current and added up all of the pieces of L that they shipped with their component kits. So if the wing kit came with 12 pieces of L, or the tail kit came with 1 piece of L, I went through the whole airplane and added all those things up and came up with a rough number of about 64. Now I'm going to have tons of cutoffs and waste from that, but if you need a 3-foot piece of L and you have to cut a foot off of it, that's just the way it is. To pre-measure, cut, and bend every piece of L in the exact length that it takes to make the plane would take forever. So Zenith used to ship this as a standard 4-foot length because you can cut a 4-foot strip of material off, bend it, and you've got your piece of L. And then if you have a little bit of waste or cut off at the end, then so be it. 64 pieces of L may actually be a lot more material than you need for this airplane. For one reason, I can't speak to what the later editions of the plans require. There may have been changes and things like that, but my recommendation at this point, if you're scratch building, is going to be just make 10 or 20 pieces at a time and use it up as you go, because of course we're not going to have the luxury of minimizing a whole bunch of waste without that taking a whole bunch of extra time if we cut every single piece to length and then form it. It's a lot easier and a lot more productive to go bend 10 or 20 of these pieces and then just cut them to whatever length you need them and go and continue assembly. But anyway, throughout the drawings here we have what's called standard L. This is basically a piece of angle that you bend made out of 25 thousandths inch thick 6061, and they give us some information here. Obviously cut to length is required. That's how you fabricate this from plans. So standard L angle, thickness 25 thousandths of an inch, 6061 T6. We can see here they've only shown us one view of the drawing. So unlike an orthographic projection where you may see 2 pieces of a drawing, they've given us enough information that we can fabricate this with just one drawing. So the developed length is 36 millimeters and the standard length is 4 feet, which is essentially the full width of a sheet of uncut aluminum that you might buy. They typically come in 4x12, 4x4, 4x2, multiples of 4 feet wide. So a full-size sheet is considered 4 feet by 12 feet. So that's one full width. And then we have a developed length of 36, which means that's the width of this piece, or the length of this piece before we fold it, before we form it. Now you notice when this is formed, it's 19 millimeters on a side. Well, 19 millimeters times 2 is 38 millimeters. Again, because this gets formed around a radius, which is a shorter distance than a hard right angle bend would be, we start out with 36 millimeters. Once the part is formed, it ends up being 19 millimeters on a side, bent at 90-degree angles with a 1/8 inch radius or 3.2 millimeter radius. Down here, it's the same story. This is standard Z angle. I think there are 4 total pieces required in the plane, maybe. Again, it's 4 feet wide. You start with a piece of 25 thousandths inch thick material, 60-61. They give you a developed length of 50 millimeters. So you start out 4 feet long, cut off a 50 millimeter wide section, and then you've got to figure out your bend angles to receive these dimensions here. Again, designated as standard Z throughout the drawings, cut to length is required. So this is Zenith telling us how to read their blueprints. So they've got some more information off to the left here that basically shows you their rhyme and reason on how their parts are denoted, what the drawing number is, the revision date. The part number example 75T2-4/0 means the aircraft model is the 750, in this case the STOL. It's T for the tail section, 2 is the drawing number, the drawing page in the tail section, so that'd be the number 2 drawing in the tail section. -4 is the actual part number on that drawing, like here, number 4, that's part number 4 is the horizontal stabilizer front bracket. And then the / gives you the revision number of the parts. Now again, this is my actual plans package with my serial number that I paid for and bought from Zenith. So no matter which aircraft you're building, there's going to be an information page just like this in your plans packet that basically tells you how to build the aircraft, what these specifications mean, how to interpret their drawings. So if you have a basic understanding of orthographic projection in the previous segment of this video that I showed you with that simple fixture block, then that combined with this information is how you move forward in building the rest of the airplane. So let's take a look at the next page in the drawing. This is going to be the start of the rudder build, and I'm not going to do a rudder build video, but I am going to use the rudder as an example on parts interpretation. So we'll get into more complicated parts later on in this series, but this is where we're going to start with the 3-dimensional interpretations of these things. For more information about the Zenith STOL CH750, please visit Zenith Aircraft Company online at www.zenithair.net. If you liked this video, please give it a thumbs up and consider subscribing to my channel. Be sure to click on the notification bell to receive all the channel updates. For additional information on the project, check out my blog at gregsplane.blogspot.com. You can also contact me directly at gregsstolch750@gmail.com. As always, thanks for watching and good luck with your projects.